My name is Yan. I'm from the University of Alabama at Birmingham. I'm the presenter of our paper, Lane Extraction and Quality Evaluation, a Hough Transform-based approach. This work is mainly contributed by Xinyao Wang, a student from the University of Michigan, who is now doing internship and cannot make it for pre-recording this video. We're happy to have our paper published in IEEE MIPR 2020, which is held virtually this year due to the coronavirus pandemic. This work studies the problem of lane recognition from each video frame image, which is important in applications such as driving assistance. In fact, lane recognition has been used in ADAS of many car models to adjust the steering wheel or give warnings if your wheel touches the lane lines. In the future technology of self-driving cars, lane recognition is also an essential first step. In our problem, we're actually detecting lines that mark lane boundaries, and we call them lane lines hereafter. There are a lot of challenges for accurate lane line detection. For example, the blue car in the upper image occludes the lane line on its right, while the lane lines in the bottom image are just as bright as the road light reflections. Another problem is with evaluations, since a small shift of the line may be considered a total error if we use pixel-level error metrics. For example, in the figure here, the white pixels are ground truth pixels for lane lines annotated by human, and the red lines are those that are extracted by our model. Intuitively, the prediction is close to reality, but the pixel-level matching result is terrible. Even worse, the annotators may not always draw the lines exactly overlapping with the actual lane lines, especially when difficult scenarios such as occlusions happen, where the annotators have to guess where the lines are based on their intuition. This introduces another source of error. So this work addresses both problems of how to extract lines from pixel-level segmentation models and how to evaluate the line matches more scientifically. We remark that our problem is different from the instance segmentation problem addressed by region proposal-based models, such as Mask RCN and YOLO V3, since our lane lines are long objects, and are also the only type of foreground object to segment. Moreover, after getting the lane line pixels, we want to extract them into lines, so that they can be compared with the ground truth lane lines more scientifically. For prediction, the geometry of the lane lines can also help in building the 3D model of the driving environment, which is important for the future autonomous driving technology. Our model design consists of two parts, one for extracting lane lines from each image, and the other for matching the extracted lines to the corresponding lane lines for more scientific quality evaluation. In stage 1, we first use GCN to extract a prediction map from each input image, where each output pixel is associated with a predicted probability that the pixel is part of a lane line. Here GCN refers to the global convolutional network, not the graph convolutional neural network that has been quite popular these days. The reason we choose GCN to extract lane line pixels is that it is designed exactly for this task. GCN adopts a large kernel that is able to capture line objects that are long. GCN is designed by noticing a confliction between the goals of object classification and localization. For classification, we often use pooling and dense layers to extract semantic features that are invariant to transformations in order to better predict the type of objects. For localization, however, the spatial transformations matter, since we would like to get their boundaries down to the pixel level. Therefore, to make our model spatial sensitive, we want to avoid dense layers and pooling layers, making the model fully convolutional. Meanwhile, we want to use large kernels so that object type can be captured from an entire object. Here's a comparison between GCN and existing models, where we can see that GCN is fully convolutional and uses large kernels. Here is a detailed model of GCN architecture, where during the encoding stage, a feature pyramid is applied to a backbone ResNet to extract image features at different scales. The feature maps are then decoded to obtain the pixel-level predictions using binary cross-entropy loss. Here in B, each GCN module decomposes a k by k large kernel into two layers of 1 by k and then k by 1 kernels for approximation, which avoids a high computation overhead caused by large kernel. There is also a boundary refinement module in C, which uses residual links to learn the incremental details on the object boundaries. So you can see the BR module here, and you can also see the GCN module here. The large kernel used is able to capture an entire long lane line to allow accurate recognition in our studied application. After we get the pixel-level probability map, we use thresholding to get a binary map where each pixel is either 0 or 1, which refers to the background or foreground pixels. The foreground pixels are the detected lane lines. We then input all foreground pixels into a Hough transform to extract lane lines, which are represented in spherical coordinates. In Hough transform, each foreground pixel corresponds to a set of lines that pass through it, or rotating around it, where each line can be represented with coordinates rho and theta, like shown here. Each line can correspond to one rho and one theta. So in other words, so for those lines that pass through a point, all these lines actually form a curve in the rho theta coordinate system. Now assume we have many foreground pixels that are on the same line, and their rho theta curves for the rotating lines around these points will overlap at the same point in the spherical coordinate system. This point corresponds to this line. In the rho theta coordinate system, if we impose a grid structure onto this coordinate system, and we can find those grid cells with a lot of overlap. And these highly overlapped points will correspond to those lanes that we extract from the Hough transform. However, since we are extracting lines using thresholding, each actual lane line can have many lines clustered around it. We will normalize them so that later data mining models in stage 2 can then group them into lane lines effectively. For the ground truth annotations that are already binary images, we can directly apply Hough transform to extract the lines. Now, let's look at the second stage, where we will extract a unique lane line from each line cluster. And if ground truth annotation exists, we will match the lane lines predicted from the input images with those extracted from the annotations to provide a scientific error estimate. Specifically, for those lines extracted from the annotation image, we will use k-means clustering to group them into k-groups, where each group corresponds to one lane line. Here, k is selected using the well-known Abel method that can almost always recover the actual number of lane lines in our annotation. We then train a k-nearest neighbor classifier that predicts the group ID of a line according to its rho theta coordinates. The trained classifier can then be used to match those lines extracted from the input image with their corresponding groups obtained from the annotation, so that we can compute the error within each group. When training the group classifier, we notice that it is necessary to conduct oversampling over minority classes, since some lane lines are perfectly annotated, leading to just one line or only a couple of lines inside one group. The image on the left shows this case, where the red line is clearly extracted since there's no ambiguity in its pixel level annotation. However, the image on the right shows that this will cause the predicted lines to be classified into the orange group, since the top k-nearest template lines are mostly orange and only one is red. Now that the lines are properly grouped, for those lines predicted from the input image that tend to be noisy, we use their group median as the representative ley lines for that group. Using median tends to be more robust to individual noisy foreground pixels predicted. In contrast, the lines extracted from annotations are relatively clean, and thus we simply use group mean as the representative ley line. Finally, since the groups have been matched due to our k-nearest neighbor classifier, we can compute the mean squared error of their row theta coordinates. We call this error as a Hough Transform based error, which reflects the similarity of lines rather than individual pixels. We have evaluated our model using the CU Lane dataset prepared by the Multimedia Lab of the Chinese University of Hong Kong. The dataset includes video frames recorded by vehicles driven by drivers in Beijing on different days. Here are some examples of the results from different stages of our workflow. Well, we can see that the extracted lines are very similar to the actual lane lines, but if we simply compare the pixel alignment, the error will be large. Here we show the comparison between our loss, which is the x-axis, and the pixel level loss, which is the y-axis. We can see that most of our loss are very small, meaning that our model performs well on most video frames. However, this cannot be reflected if we use a pixel level loss, since for the same line level error, we can see that the pixel level error can vary a lot and can be very large. A weakness of our method is that evaluation stage is not integrated end-to-end into the neural network training, but during training, we can compute our line level loss on the validation set to obtain a more accurate estimate of when our model begins to overfit during training. Histogram of how many video frames are at each error range for both our line level error and the pixel level error. And we can see that our line level error is very clustered and close to zero, while the pixel level error scatters over a wide range and is not indicative of the real performance of line extraction. This ends our presentation, and thanks a lot for your attention. If you have any questions regarding this work, please feel free to contact Xinyao Wang, who is the first author of this work.